In this video, we're going to talk about families of functions, transformations, and symmetry. I'm going to go over some very basic functions, and then you're going to see some more complicated functions where you're going to basically do the same thing as I do in these two functions here. I want you to be able to graph the functions. I want you to be able to find a domain range where it's increasing, decreasing, constant, and we're going to talk about some symmetry by the end of this video. All right. And so one of the simplest functions is called your constant function. The reason why it's called a constant function is because it's f of x equals some number, right? Or some constant, some real number, some constant. And so the general form that we could use for this is f of x equals k. Well, if that is the case, then we know that since f of x is the same thing as y, and when we have y equals some number, so k is some real number, that is just a horizontal line, right? So I'm going to do an example. Let's just do f of x equals 2. Then the graph of that function looks like this, right? That's f of x equals 2, right? F of x equals -2 is just a horizontal line that goes through a y-intercept of -2, so on and so forth. Right? The domain of this function is going to be always -infinity to infinity. It is parallel to your x-axis, so it encompasses your entire real line. And the range of this function is always whatever y value is your y-intercept, or whatever that constant your function equals. Just to give a general form for this, it's going to be just that value k, right? So for in our example, this k is actually 2 because that would all the points on your graph of this function have a y value of just 2, all right? And so all the y coordinates to the points on this graph are going to have a y value of k, all right? This function is not increasing. It is not decreasing. It is completely constant, and it is constant on the entire interval, the entire real line, right? So if x1 is less than x2, then the y values are going to be exactly equal. So it's constant from -infinity to infinity, right? So this is one of our simplest functions. We'll come back to symmetry later. All right, this is a linear function, right? But we call it constant because your y values remain constant, all right? Other linear functions that are not constant, we call them linear functions. So we use the word linear with those, but we use constant for that one, even though that one is still constant. All right. And it's f of x equals mx plus b. All right. Now, m is your slope, b is your vertical intercept. And some things with this graph is going to change, right? I'm just going to give an example. For instance, f of x equals 2x minus 1, right? My vertical intercept is -1. So I plot that point, I go up 2 into the right one, or I can go down 2 into the left one, and I'll have a point that's on that graph, right? So I can draw my line, which looks like that, and I have my function, all right? Now, any of these functions where m does not equal 0, because if m equaled 0, we would be having a constant function, which is over here, then it's going to be a slanted line, right? It's going to have a slant. It's not going to be horizontal, and we know that a vertical line is not even a function anyway, all right? So the domain of that function, since it's a slanted line always, is going to be from -infinity to infinity. And the range is also going to be from -infinity to infinity, right? And any slanted line is going to continue going up and down and right and left indefinitely. So our domain and range are both all real numbers. Depending on the slope, right? So it's increasing from -infinity to infinity if our slope is positive, all right? That's if the slope is positive, right? Or is decreasing from -infinity to infinity if our slope is negative. Okay, so depending on which linear function we may have that is increasing and we may have that is decreasing. It will never do both because a line can only have one type of behavior, and it's a constant rate of change. It never changes. And so it's either going to be that or that. And the example that we have here is increasing. And so we're in the case here. Linear functions where m does not equal 0 are never constant, right? So the constant part will be not applicable, all right? Another type of function that we want to talk about is actually a stepwise function that's called the greatest integer function, all right? It's a stepwise function, meaning we could actually, it looks like some steps when we graph it, but it's a piecewise function as well. But since it's an infinite piecewise function where we can't write out all the pieces, we have this special notation for it, and we give it a special name. The greatest integer function is denoted f of x equals, there's a square bracket, but there's double bars, double vertical bars in order to make that square bracket, all right? This is the greatest integer less than or equal to x function, right? So it's the greatest integer less than or equal to x. The way I like to think about it, right? If I have a number line, the largest integer that's less than or equal to x, right? So say I have a number like a half. Well, on my number line, a half is here. So I want to find the biggest integer that's smaller than a half, that's less than or equal to a half. Well, the biggest integer is 0. So the greatest integer evaluated at 1/2 is 0. Okay. I'm going to extend this number line so that it includes larger numbers. The second one is 6.5. All right, 6.5 is halfway between 6 and 7. The largest integer less than or equal to 6.5 is 6. So my greatest integer evaluated at 6.5 is 6. Negative 1/3. Negative 1/3 is between -1 and 0. The largest integer that's less than or equal to, that's smaller than, less than numbers that are less than a number are always to the left, right? That's less than or equal to -1/2 is -1. So my greatest integer function evaluated at -1/3 is -1. And then at 2, my greatest integer less than or equal to 2. Oh, there's an equality on that less than or equal to. So this actually equals 2. All right. So basically what this function does is it rounds any number down, but it keeps a whole number exactly the same way it is, right? So evaluated at the whole number 2, you don't round down because 2 is a whole number, right? It's already an integer. So the greatest integer evaluated at 2 is 2. But if I pick any number between 1 and 2, it's going to round down to 1. Even the greatest integer evaluated at 0.9, well, sorry, 1.9. 1.9 is almost 2. But the greatest integer function basically means we select the largest integer less than or equal to 1.9, which is 1. All right, and so let's talk about the graph of this function, right? Now we have some x coordinates and y coordinates, right? Because when we input a value, we can always find the largest integer that's less than or equal to that value, right? For instance, any number that's between 0 and 1, so my x-axis is here, 0 is here. Any number between 0 and 1, if we evaluate it into our greatest integer, into our greatest integer function, all right? Any number between 0 and 1 is going to have an output value of 0, right? So our function is constant between 0 and 1. And it equals 0 at 0. So I'm going to put a closed circle at 0. Now, if I were to input 1 into our greatest integer function, the largest integer less than or equal to 1 is 1. So I need a closed circle here, right? That means this one is going to be open or I wouldn't have a function. That's closed. And then all the values between 1 and 2, like 1.1, 1.2, 1.3, 1.4, 1.5, the largest integer that's less than or equal to that is 1. So all of those points between 1 and 2 are going to have a y value of 1. So we get another constant line here. All right. At 2, the largest integer less than or equal to 2, which we found above, was 2. In order to make this a function, I'm going to make sure that I make you aware that this is an open circle here. And so there's a pattern, right? We're just going to get a bunch of steps for all of the numbers that are between your integers. And at your integers, you take on the y value, your y value is the same as your x value, right? And so the same thing happens for negative values. And so we get a function that looks like this. And this is why we call this a stepwise function. Okay. All right, so the domain of this function, it is actually all real numbers, right? All of these points here have a x value between -5 and -4. It's open at -4, but this point right here closes it at -4, right? So that's -4 is still included. This part of my graph has values between -4 and -3. So all of these are in my domain. At -3, I have this part, this step of my function. And it continues on forever and ever. And so our domain here is all real numbers, negative infinity to infinity. Our range, however, is different. Our output values are all whole numbers. And in fact, I can't just use the word whole numbers, it's their opposites as well. So they're all integers, right? So it's the set of all integers, which we use as the double barred Z. All right, you can use the word as a set of all integers. This function is not increasing, this function is not decreasing, and it is constant at various areas here. So that's not applicable. But it is constant, and I'm going to write this in this manner here. It is constant on intervals from, like, for instance, 0 to 1, right? I include the leftmost point, but I don't include the rightmost point, right? So it's the set of all intervals that look like this, such that x is an element of the integers, right? So for instance, it's constant between 0 and 1, right? So if I use the integer 0, I have the interval from 0 to 1, right? Our function is definitely constant there. If x equals 1, I'll replace 1 in for x and y, then I'll get 1 comma 2, right? It's constant on that interval. If I let x equals 2, I'll get this interval here. That's from 2 to 3, right? And so I'll never ask you to write this, but this is one way that we could write the interval on which your function is constant. All right. These are 3 functions that we'll visit, or I want to introduce you and put into our family of functions that you want to be familiar with. There are probably about 8 or 9 more that we're going to look at, but get familiar with these functions because what we're going to do is we're going to have to be able to work with these functions very well. And one of the ways that we're going to work with these functions is to be able to graph them, all right? These are the most basic functions. They're in the library. Some people call these parent functions, all right? We get more complicated functions from these functions that are in our library by doing transformations of them, right? So for instance, y equals x squared is going to be in your family of functions. And so I'll have you look at the graph and tell me the properties of that function. But sometimes we want to be able to graph something like y equals 2x minus 4, and I'm putting x minus 4 squared plus 7. We want to be able to graph a function that looks like that. And we don't want to have to rely on a calculator to help us graph that. And so one way to do that is to learn about how we can transform these functions graphically. And so whenever we have a parent function or a function that's in our library of functions, we can do some things to that function. We can add or subtract a number to our x in the input part of our function or in the inside of our function, right? We can add or subtract a number outside of our function, and we can multiply a number on the outside of our function, right? So when I look at y equals x squared, what's done to the x is your actual function, right? So some people call this a quadratic function. I like to call it the squaring function because what we're doing to the x is we're squaring it, right? We're squaring all of our input values, right? When I see this minus that's close to x, what this does to that function is going to look like that if I have my real function. But what it does is it translates that function or slides it or shifts it either to the right or to the left. All right. Now, when h is greater than 0, the shift is to the right. And when h is less than 0, it shifts it to the left. All right. It shifts it to the left. And so when I see this here, Notice there's a minus here. So when I see a minus, that means, and I see a number, that means that's a shift to the right, right? So if I look at y equals this 2x minus 4 squared plus 7, that's just shift 4 units to the right. All right. I know when you see a negative, you think left. That's not the case here. All right. Sometimes we'll have a negative number multiplied on the outside of our function. That is not the case in this one right here, right? But if that were a negative 2, I would say that that's the case. Basically, this is equivalent to multiplying all of your y values of your function by a negative, multiplying your y values by a negative. Well, if I multiply any value that's above my x-axis that's positive by a negative, it's going to go below the x-axis. And so we call this a reflection because the graph is going to become a reflection about the x-axis. When there's a number multiplied on the outside of a function, like this 2 in this example here, multiplication of a number actually either stretches that function or it shrinks it, all right? And this is all vertically because it's done to the outside of the function, right? So it's going to stretch it if a is greater than 1. So we're going to stretch by a factor of a. And if a is a fraction, now we already know what happens to the negative, right? If the negative is multiplied out front, it's going to reflect about the x-axis. That's what we have here. But so we're not talking about anything less than 0. We're just talking about positive numbers now. All right. And so if it's bigger than 0 but smaller than 1 or something like a half or 0.6, then it's actually going to be a vertical shrinkage. So it's going to shrink our graph by a factor of a, all right? And then last but not least, sometimes we can add a number to the outside or add or subtract a number to the outside of the function. And so that's like that 7 here, that positive 7 there. If you add a positive number, if a is greater than 0, you're going to shift up. If it's less than 0, you're going to shift down. And the reason for that is because there's a plus sign there. So whatever sign that the k has, you're basically going to add that to your y values or subtract it from your y values if it's negative. Notice each of these 3 things here are vertical. They're done outside of the function, right? This negative is multiplied on the outside of the function. This a is multiplied on the outside of this function. And this f of x is added on the outside of your function, right? This is horizontal because it's done to the inside of your function, right? So as I call this y equals x squared the squaring function, you know that something is inside if it's done to the operation that your function has, right? So since I have our squaring function, I know that this is a horizontal translation because it's done before we square it. It's on the inside of the function. All right, let's get used to this. And so we're going to write the equations that are described below. It says the graph of y equals the greatest integer less than or equal to x is translated 5 units to the right and 2 units down, right? Well, when I move something right and down, those are both translations, right? So that's the translation and that's the translation. When I move something to the right, that's a horizontal translation and it's going to show up in this form right here. So what I've got to do, if it's to the right, that means that h is greater than 0. Then when I write my greatest integer function, it's going to be an x minus 5 instead of just an x in that greatest integer function. All right, so that takes care of the 5 units to the right. And then 2 units down, all right, so I'm going to add k. When k is greater than 0, we shift up. If k is less than 0, we shift down. So I'll add a -2. And if you don't want to write plus -2, we know that that's -2. So I have that there. So this will give me the graph that's described here. It says the graph of y equals absolute value of x is stretched by a factor of 3, translated 5 units upward, and reflected in the x-axis. All right, so we're going to do each of these 3 things in order, and then we're going to come up with our function. All right, so we have y equals absolute value of x. It's stretched by a factor of 3. My stretch is a multiplication. So I know I'm going to have a 3 multiplied on the outside of my function, right? That's vertical, it's on the outside. 5 units upward, that's on the outside, and reflection about the x-axis, all right? So I'm going to do it in the order that they tell me. So it's stretched by a factor of 3. That means I multiply by 3. I translate 5 units upward, so I'm going to add 5 to the outside, like this k. And then it's reflected in the x-axis. That means I take what all I have, and I multiply it on the outside of that function. So I have y equals -3, absolute value of x, minus 5, because I need to distribute this -3 to both of those terms. And there is the function that is described here. Now, although I did this in this order, all right, generally when we graph a function using transformations, we want to do our horizontal translations first, our reflections, our stretches, and then our vertical translations, all right, in that order. I'm going to use this order because it kind of follows the order in which the operations are done from the inside function out. And that's how we want to do these transformations. Let's look at an example. It says use the transformations to the graph of the function to obtain the graph of the function. And then we're going to state the domain. So I have y equals -square root of x plus 2, and then we have -4. All right, we're going to learn that the parent function or the function in our library of functions is y equals the square root of x. You want to get very comfortable with this graph, all right? I'm going to graph it, right? And I'll do some extra stuff for you. We can't, if we plug in a negative number, we're not going to get a real result. I'm going to plug in some points, right? 0, the square root of 0 is 0. The square root of 1 is 1. The square root of 2 is not a whole number, so I'm going to leave that point off, right? The square root of 4 is 2, though. All right, every time I graph using this method, I'm going to try to use at least 3 points. You can use more, but I'm going to go ahead and graph these points. I had a point 0, 0, 1, 1, and 4, 2. And so when I graph these, I get a graph that looks something like that. All right, there's my graph. And so what I want to do is I want to be able to graph this function, which is a much more complicated version compared to this function here. However, it's easy, right? So if I look at this function, I'm going to look from the inside out. The thing that's done to the x first is that +2 there. That +2 means that I take this, I'm basically having this thing right here. That's the first thing that's done to my x. That's a shift left 2 units. So what I'm going to do is I'm going to go to all of these points, and I'm going to shift every point to the left 2 units, right? So I'm going to get the point -2, 0. I'm going to get the point -1, 1. And if I shift this one 2 units to the left, I'm getting the point 2, 2. I'm going to draw that graph, and I get a graph that looks something like that. And let me use some good graphical procedures here by actually labeling my points. Okay. All right. That's not my final graph. The next thing that is done for me to get to this is that negative is multiplied, right? So what I'm going to do is now I'm going to look at this, -square root of x plus 2. Well, when there's a negative on the outside of the function, because this is a square root function, that means that's a reflection about the x-axis. And basically, I'm going to take all the points here and multiply them by this -1, right? So I'm going to have different signs. So the point -2, 0, oh, it stays the same, because if I multiply 0 by -1, it stays the same. -1, 1 would be -1, -1. Negative, and then 2, 2 would become 2, -2. So I have the point -2, 0, -1, 1, and then I have the point 2, -1. Oh, that's a -1, -1. So I look at my graph, and I get something like that. And just so that this stuff will fit on the graph, I'm changing this up completely. I'm changing that to a +4. Sorry about that. I'm changing this to a +4 instead of a -4. All right. And so what we're going to do here is we're going to graph our final graph, which is y equals -square root of x plus 2 plus 4. I don't have space there. And so what I'm going to do is I'm going to take all the points from that previous graph, and basically I'm adding 4. So we're going to go up 4 units. I'm adding 4 to all of the output values of this graph right here. Notice the +4 is outside of that square root. And so I'm going to put this on my final graph here, which is to the right. So the point -2, 0, 0 plus 4 is 4. So I get the point -2, 4. -1 will become the point -1, 3. And then the point 2, -4, -1 would become 2. Oh, that should be a -2 there. I am so sorry. That's 2, -2. So if I add 4 to that, that would become the point 22. And I've been using black. And so if I draw that graph, it looks something like that, right? So now let's find a domain. Well, the domain is from left to right. My leftmost point on my graph has an x-coordinate of -2, and it extends indefinitely to the right. And my range, since my graph continues this way, it's going to continue to go down. So I'm going to go from -infinity, and I do have the highest point, which has a y-coordinate of 4. And that will be the graph of my function. Remember, you could always... I made a mistake, didn't I? Right? So stuff here, right? Your professor still makes mistakes, right? This is the point 22, right? And so instead of having my graph look like that, I'm going to correct this mistake here, right? It's the point 22. Yeah, and then I'll draw my graph here. And I knew it was stretching a little bit, but there we go. So this is our final graph here. What I did doesn't change the domain and range. So my domain is going to go from -2 to infinity. And then my range, so this -2 is the x-coordinate to this point here, which I have here. And then my range is going to go from -infinity to 4. Notice you put the -2 in brackets and the 4 in brackets because those are included. All right. We want to talk about some symmetrical properties of graphs. And so if I look at, there are 2 types of terms we deal with when we're talking about the symmetry of functions, whether functions are even or odd, right? A function is even if it has symmetry with the y-axis, right? It has symmetry with the y-axis. All right, this function that I see right here is y equals absolute value of x, right? So that's my function, y equals f of x, or f of x equals the absolute value of x. It is an even function, all right? Now, we may not be able to always graph these functions, and so we want to be able to test whether a function is even or odd or neither using some algebra. And the way we do that is to look at the properties of these functions here, right? So for instance, I'm going to pick an x value. This is x, and over here, it'd be -x, right? I went the same distance from the origin to the right and the same distance from the origin to the left. Now, I didn't label this, so it's in any x value. It could be 3, it could be 30, whatever. But this is my x, and if I go the same distance to the left, that's -x. And it just so happens that that functional value is exactly equal, because it's symmetric with respect to the y-axis, exactly equal to that functional value there, right? So these 2 points, these 2 y values are the exact same y coordinate. They're equal. So one way to test whether a function is even is if you plug in the -x, you get the same value that if you'd get if you plugged in a regular x or a positive x. That's true about even functions. Odd functions have symmetry with respect to the origin. Symmetry with respect to the origin is a little bit more difficult to think about. One way to think about it is to take a part of your graph in one quadrant and reflect it about both the x and the y-axis, right? So for instance, if I took this part of my curve in the first quadrant and I reflected it about the x-axis, I would get a graph that looks something like that. And then if I took that part and reflected it about the y-axis, I would get this part of my graph over here. That means I have symmetry with respect to the origin, all right? The test for that is a little more difficult to think about. So I'm going to pick a point here, x. Then if I go the same distance from my origin, but in the opposite direction, I'm going to get a y value, right? So this functional value on this, that's f of x, this functional value is f of negative x. It just so happens that these two are the same number in absolute value, all right? But they're opposite signs, right? This one's above the x-axis, this is below the x-axis. And so if I want to test, then this means that the functional value evaluated at the negative x is the opposite of the value I get when I plug in the positive value, all right? And so this is the test. Let's put this into practice. Determine algebraically, that means we want to see some work, whether the function is even, odd, or neither. Notice that the test always starts with plugging in the negative x, right? And so I'm going to plug in or replace x with negative x. So everywhere I see an x, I'm going to replace it with negative x. Well, negative x to the fourth power, 4 is an even exponent. Having that negative there doesn't matter. So that's the same thing as x squared. Or you can think of taking -1, raising it to the fourth power, or any even power, you're going to get the positive value anyway, right? So that's still x to the fourth. Here, the same thing happens. Since 2 is even, then I have that right there. And so since this is the same thing that I started with, which was f of x, then this satisfies the quality that my function, or the test that my function is even. So I can say that this function here is even. All right, let's look at this function here, right? So we're going to do the exact same thing. We're going to start off by doing the same thing. Let's replace x with negative x. And when I do that, negative x squared is just an x squared. So I can kind of ignore that negative, right? Because if I square it, it's going to be a positive. But when I have an odd power, this is the same thing as saying negative x cubed, right? And 3 times a negative x is a minus 3x. So notice here, this is not the exact same thing that we started with. However, I could factor out that negative in my denominator. And if I factor out a negative out of both of those, they both become positive. So I need to put a plus sign there. And notice if I divide something by a negative, I can just bring that negative out front. And I get the opposite of what I started with, right? That's the negative of f of x. And so by the test for an odd function, I can declare that this function here is odd. All right. And so what I want you to be able to do is either be able to look at a graph and determine if a function is even or odd or neither, or you can look at plugging in and using that test. Now, if we come back to this example here on the first page of our notes, we can see that this has symmetry with respect to the y-axis. So this is an even function. And we can see here that this one in and of itself, this specific one, does not have symmetry with the the y-axis or the origin. And so this one right here, specifically on this graph, is neither even nor odd. So it's neither. All right. And so this concludes our video. I'll see you next time.